In this lecture, we will set up the double integral for the surface area of the portion of the plane minus 3x over 2 equals z that is inside the hyperboloid 25x squared plus y squared minus z squared equals 1. The hyperboloid 25x squared plus y squared minus z squared equals 1 is a hyperboloid in one sheet. When we intersect this hyperboloid with planes that are parallel to the xy plane, that is, for each fixed value of z, the level curves of the hyperboloid turn out to be ellipses. The surface whose area we are after is a portion of the plane minus 3x over 2 equals z. It is the portion of the plane that is inside the hyperboloid, and so it is bounded by the intersection curve between the hyperboloid and the plane. We remove the hyperboloid from the image to get a better view of the surface. In order to come up with a double integral for the area of the surface, we come up with a formulation for the surface. Since the surface is part of the plane minus 3x over 2 equals z, we can write z as a function of x and y, and so we let f of xy be equal to z. However, we will take a slightly more general approach in that we will use a parameterization for the surface. Suppose that we represent the surface by the vector function r of xy, which is equal to the vector x, y, z of xy. As such, the surface area is equal to the double integral over the surface of the magnitude of the cross product of r sub x and r sub y integrated with respect to x and y. Z of xy, or f of xy, is minus 3x over 2. R sub x, or the partial derivative of r with respect to x, is the vector function 1, 0, z sub x. R sub y is the vector function 0, 1, z sub y. The cross product of r sub x and r sub y is the vector function minus z sub x minus z sub y 1. Or, if we use f of xy equals z, the cross product would be minus f sub x minus f sub y 1. The magnitude of the cross product is equal to the square root of the square of z sub x plus the square of z sub y plus 1. Differentiating z with respect to x, we get z sub x equals minus 3 halves. Z does not depend on y, and so z sub y is equal to 0. Therefore, the magnitude of the cross product is the square root of the square of minus 3 halves plus 0 plus 1. This is equal to half the square root of 13. We can bring this constant out of the double integral. Therefore, the area of the surface is half the square root of 13 times the double integral over the surface integrated with respect to x and y. We just have to choose the order of integration and the corresponding limits of integration. Since we are integrating with respect to x and y, we need to project the surface onto the xy plane. We get the projection of the surface on the xy plane by pushing the surface directly onto the xy plane. The magenta curve represents the boundary of the surface. The blue curve, which is supposed to lie on the xy plane, is the projection of the magenta curve. Changing the perspective, this is what the projection of the surface should look like. We will see in a moment that the projection on the xy plane of the surface is indeed an elliptical region. In order to find the limits of integration, we must find an equation for the bounding curve of the projection. The boundary of the projection corresponds to the intersection curve between the plane minus 3x over 2 equals z and the hyperboloid. To find an equation for the magenta curve of intersection between the plane and the hyperboloid, we replace z by minus 3x over 2 in the equation of the hyperboloid. Simplifying this equation, we get 91x squared over 4 plus y squared equals 1, which is indeed the equation of an ellipse. This is equivalent to the equation 91x squared plus 4y squared equals 4. If we integrate with respect to x first, then we must follow the x direction within the projection on the xy plane. We must determine from which curve to which curve the projection goes. Most importantly, because x is the first variable of integration, we must express x as a function of y on these bounding curves. The projection goes from the left half of the ellipse to the right half of the ellipse. We solve for x on the ellipse and find that for the left half, x is equal to minus 2 times the square root of the quantity 1 minus y squared all over 91. For the right half, x is equal to 2 times the square root of the quantity 1 minus y squared all over 91. And so we have the limits of integration for x. Y is the second variable of integration, and so we solve for the minimum and maximum values of y within the projection. The absence of linear terms in the equation of the ellipse tells us that the ellipse is centered at the origin. Therefore, the minimum and maximum values of y correspond to the y-intercepts of the ellipse. We set x equals 0 in the equation of the ellipse and find that y is plus or minus 1 at the intercepts. And so we have the first double integral for the surface area. If instead we integrate with respect to y first, then we must follow the y direction within the projection. This time, the bounding curves are the lower half and the upper half of the ellipse. Now that y is the first variable of integration, we must solve for y in terms of x in each of the bounding curves. Solving for y on the ellipse, we find that y is equal to plus or minus the square root of 1 minus 91x squared over 4. And so we have the limits of integration for y. With x as the second variable of integration, we look for the minimum and maximum values of x within the projection. The minimum and maximum values of x correspond to the x-intercepts of the ellipse. Setting y equals 0 in the equation of the ellipse, we find that the x-intercepts are at x equals plus or minus 2 divided by the square root of 91. And we have the second double integral for the area of the surface. We leave it as an exercise for the viewer to carry out the integration and find the exact value of the surface area. Actually, one can find the exact value of the surface area without having to carry out any integration at all. First, observe that the integrand for both integrals is 1. And so each double integral without the square root of 13 over 2 is simply the area of the elliptical region. For the area of an ellipse, we just need the semi-major and semi-minor axes. The area within the ellipse is equal to pi times the product of the semi-major and semi-minor axes. And so the area of the elliptical projection on the xy plane is equal to pi times 1 times 2 divided by the square root of 91, or 2 pi divided by the square root of 91. To get the area of the surface, we multiply the square root of 13 over 2 to the area of the elliptical projection, and get pi over the square root of 7 for the surface area.